This video is on the objective make a conclusion and interpret the results of a one-mean hypothesis test using the critical value approach. Now this is with a known standard deviation. Right, so because sigma is known, the population standard deviation is known, we're going to be using this a standard normal we're going to be using a normal distribution, and z-scores our critical values will be z-scores. And this is number 1, right? So this is the first video on this objective question in your Newton-Alta homework. So let's take a look. All right. So here again, now this is just the step where you make a conclusion and interpret the results. So they kind of go through and do a lot of the steps for us. I'm going to actually write out myself what steps I would take to perform a hypothesis test, because we're going to eventually have to do all the steps ourselves. So here, Gavin is a healthcare economist who expects that the average cost of a visit to an urgent care clinic is more than that of a physician's office of $55. So more than $55. He suspects the average cost of a visit to urgent care is more than $55. So after calculating the mean and standard deviation for the cost of 100 of urgent care visits, so this is a sample, and using a significance level 1%, so that's your alpha, right? 0.01, 1%, and works through the testing procedure. Now he has all this here. I'm gonna also write this out. Right? Go through the steps of a hypothesis test. All right. So first, there's always a claim being made, a claim being tested, and this claim is about a population. Now I'm going to have mu here because it mentioned average, right? Mean. I'm going to have mu be the average cost of an urgent care visit for the entire population. So average cost of all urgent care visits. So that's what mu represents. And then the claim, what this particular person expects or suspects. They expect the average cost of a visit to an urgent care clinic is more than $55. So the claim here that's being tested is that the mean value, this average cost, this mean of all urgent care visits is greater than 55 or greater than $55. Now this does not involve equality, so this will be represented by the alternate or the alternative hypothesis, right? Then you set up your hypotheses. Null hypothesis H0 and alternative hypothesis HA. This is going to be represented by the alternative hypothesis, right? So I'll just put mu is greater than 55. And then remember, once one of these is established, the other one is the opposite. Mu is less than or equal to 55. But what we're going to be assuming from this, and usually what's written or what's going to be written in this book, in the Newton-Alta stuff, you're just going to assume the equal part. We're going to assume that mu equals $55, right? So we'll assume this, right? That the population average is $55. And we're going to test that against the population average being greater than $55. Right. So a claim is made, hypotheses are formed. Also, the way look at how the alternate hypothesis looks. This is the parameter is greater than a given value. So what we have here is an example of a right-tailed test. All right, this is right-tailed, and I'm going to keep that in mind for later when we find critical values and a critical value and set up a rejection region. All right, and then after the hypotheses are set up, you know what kind of a test you're running, right-tailed, left-tailed, or two-tailed. then usually a significance level is identified. Now, if it's not mentioned, just assume it's 5%. That's a reasonable significance level. But this one is mentioned, right? And this is alpha. They told us it was 1%, right? So 0.01, a 1% significance level. Okay, now a sample is taken. Right? A sample is taken from the population. He takes a look at so many urgent care visits, and say he looked at 100 of them. Right? So the sample size is 100. And from those 100, the sample mean, the average cost of those 100 urgent care visits was $56. Now, this is one of those few cases where we know the population standard deviation. Right? Sigma is known here, and sigma is told to us, and it's back on the page, back on the website. They say sigma is $6.2. All right. So because sigma is known, by the central limit theorem for means, if we were to look at all possible samples of size 100 and look at their averages, the average costs for all possible samples of size 100, the distribution of those averages would be approximately normal, with a mean called mu sub x bar and a standard deviation sigma x bar, where the mean of these means is the mean of the population. And looking back at this is where the null hypothesis comes in. We are assuming the mean of the population is $55. Okay, so this is coming from the assumption in the null hypothesis. And the standard deviation of these sample means for samples of size 100 is, remember, the standard deviation of the population divided by the square root of the sample size. So that'd be $6.2, that was known, that was given to us, divided by the square root of 100. Well, that's just 6.2 divided by 10, so 0.62. Right. And then I'll draw a little picture. There's a number line representing possible values of x bar for samples of size 100. We know that the x bars are normally distributed, right? So I got a nice symmetrical bell-shaped curve. Then under the peak, right, on the number line is the mean value of these x bars, which we said was 55, right? That's what's being assumed from the null hypothesis. So we assume that the mean was 55. And the standard deviation is about 0.62 here, so these inflection points, remember the inflection points should be one standard deviation above and below. So this is about 55.62, and this one's 54.38. Right. So there's one standard deviation below, one standard deviation above, and being a normal distribution, remember that means about 68% of the area is in between these two, if you recall your empirical rule. Right. Now, what we're doing is we're going to decide, if we assume that the mean is 55, right? If we assume the population mean is 55, is our sample mean, is our sample mean close enough to 55 to where we can think that that's a good assumption? Because if this sample mean is pretty far away, well, then there's a good chance that this assumption is wrong, right? And we would reject the null hypothesis. So 56, that would be, let's say, somewhere over here. Now, here's our sample mean, 56. There's our x bar. Right? Now the question is, how many standard deviations, how far away in terms of standard deviations is this value? How many standard deviations away from the mean is 56? So we convert everything to z-scores. Right? This is a normal distribution. So what I'm going to do is, called normalizing. Right, so we normalize, change it to z-scores. So now I'm looking at, remember the standard normal, z, had a mean of 0 and a standard deviation of 1. Right. So again, still the same looking curve. But now, the z-score for the mean for 55 would be 0. The z-score under these inflection points would be 1 and -1, right? Because again, these values under the inflection points are 1 standard deviation above and below the mean, so they'd have z-scores of 1 and -1. All right, the question is, what's the z-score of 56? So I'll call this z-test, right? And this was our test statistic. You took from the sample, you calculated a test statistic. So again, I'm calling this z-test. And this is just the z-score for our sample mean, in the distribution of x bars, in the distribution of all sample means for samples of size 100. So I take 56, my sample mean, subtract the mean value, right, minus 55, divided by that standard deviation, right, this 6.2 divided by the square root of 100, the 0.62 there. And I'll round this to like 2 decimal places. So I'm going to pull a calculator up. All right, so we have 56 minus 55 is 1. So I have 1 in the numerator divided by, that 0.62. So the z-score for our sample mean of 56 is about 1.61. Right, so that's approximately 1.61. There's the z-score for our sample mean. That's called the test statistic. Right. So after the test statistic is found, then it all, depending on what approach you're using. Now we are using what's called, the critical value approach. Now this is a right-tailed test. We saw that earlier. Right-tailed because of how the alternative hypothesis looks. So now so there's only one critical value, right? This is a one-tailed test, right tail. So now I'm going to find what's called, again, the critical value for this test. So we're looking at, again, the standard normal now, right? We're looking at this z distribution, right, with the z-score of that 55 earlier was 0, right? The middle is 0. And what we're looking for, remember alpha here was 1%, that significance level. We are looking for what z-score has 1% to the right. Right. And it's got to be to the right. It's a right-tailed test. Area equals 1%. So the way they label that, the z-score with 1% above it, that's that z with a subscript of 0.01. Right? Remember the little z-scores with the subscripts. That's the z-score with an area of 1% above it. Now, I could find this with my calculator or a table. Now, I'll show you the table in a second, but we go to the calculator. Remember how to find a z-score, given an area? You use that distributions and then went to inverse norm. Now, that area you're entering on the calculator is area to the left, right? So if I want the z-score with 1% above it, that's got 99% below it. So I'm going to enter 0.99 there. And then mean 0, standard deviation 1. Okay. So it's approximately 2.326. All right, so that's 2.326. So this is separating the rejection region from the this area with the 1%. This would be called my rejection region. So if our test statistic is more than 2.3626 standard deviations away from the mean, then we'll reject the null hypothesis. We'll reject that assumption that the mean is 55 and say, oh, it probably isn't 55 because my sample ended up being so far away. Well, let's see. Remember, our test statistic ended up having a z-score of less than that, right? It was 1.61. So not in the rejection region, right? Z test here is less than our critical value. Right? So we're not going to reject, right? We're going to fail to reject the null hypothesis. Right? We won't reject the assumption that the mean value is 55. All right, we'll accept that. So we're going to eventually conclude later that, you know, we're accepting the statement that the mean is $55. So we're not going to accept the claim that the mean is greater than $55. Right? We're not going to accept that claim. We're not going to accept the alternative hypothesis. Right. All right. So back on the website though. See, they went through all that. They told us the hypotheses, sample information. You know, sigma is known here. They gave us the significance level. They even went through and found the test statistic for us, 1.61 as I mentioned. And they found the critical value, right? That z-score with 1% above it, 2.326, as I mentioned from the calculator. Now the question is, conclude whether to reject or not reject the null. Well, I mentioned, you know, this test statistic for our sample, right, 1.61, is not in the rejection region. It's not greater than or equal to the z with 1% above it. It's not greater than or equal to this critical value. So we don't reject. And then based on this context and the null and alternative hypotheses, what type of hypothesis test should be used? All right, so here we got one of these interactive guys where I got to move, you know, we said it was a right-tailed test, right? So I move this down to, come on, right-tailed. There, right-tailed. And then I guess I need to move this purple dot so that the z, you know, the critical value is at 2.326. There it is, right? There's the critical value, 2.326. Oh, all right, so it just said move. All right, so I think there might be multiple parts to this. All right, move the blue dot to choose the appropriate test. So we did that. Right tail test. Okay, good. And I think there's probably more to it. Okay, so we did that. All right, and then I think continue, it's gonna, yeah, more to it, right? And then, all right, then we just talk about, now remember I said earlier, our test statistic was 1.61. 1.61, which is to the left of this critical region. We're not critical value. We're not in the rejection region. So I would fail to reject the null. I would fail to reject the null hypothesis. Less than, I don't know why is this alpha over 2. This shouldn't be alpha over 2. Yeah, this should not be alpha over 2. There's a typo here, but still, we would fail to reject the null. And, you know, that means there is not enough evidence to reject the null hypothesis that the mean cost of urgent care visits is more Now, that's not what the null hypothesis is, though. But still, there's not enough evidence to reject the null hypothesis. All right, so we would keep the null hypothesis that the mean is 55, and we wouldn't accept the claim that the mean was greater than 55. Yeah, and the test statistic does not fall within the rejection region. So those two go hand in hand. All right, the fails to reject and the test statistic does not fall in the rejection region. Those go hand in hand. And the reject the null and the test statistic falls within the rejection region. Those you're going to collect. You know, those go hand in hand as well. And again, please read through your answer explanations, whether you get it right or wrong. All right, if you get it right, read through it, make sure your reasoning was right. If you get it wrong, definitely read through it to see if you can figure out what went wrong, and then next time you see a problem like that, you can do better. And I think that's it for this type of problem. No, there's one more question. Okay. So based on your answers regarding Gavin's study, regarding the cost of urgent care visits compared to physician office visits, choose the correct conclusion that interprets the results within the context of the test. Now, the conclusion should always be about the claim. All right, and the claim here was that the average cost of all urgent care visits is greater than $55. So let's see what this first one says. There is not enough evidence, right? There's not sufficient evidence at the 1% significance level to conclude that the average cost of a visit is more than $55. Yeah. All right. Because we didn't reject the null. All right. I'll bring up my paper again here. Going back. That means we kept this. We didn't reject it. That means we reject this, right? And this was the claim, right? This was the claim. So that means we're rejecting the claim. There's not enough evidence to support the claim if we didn't reject the null. Right. So that's what this first statement is saying. There is not enough evidence at this 1% significance level to conclude that the average cost of a visit to urgent care is more than that of $55. This is the opposite of that statement. And then let's see, select all that apply, so more than one of these might also apply. This is a right-tailed test, right? And the test statistic is less than the critical value on the right side. So we fail to reject the null. That's exactly what happened. So I'll select that as well. Yeah. Okay, great. I think both of those will apply here. Wonderful. Both of those are true. I think that might be the last part of this question. Let's see. And yes, it is. Okay. So, and hopefully watching that, it's a lot of stuff, right? And you've seen it. You've seen the steps listed off before. Claim, hypotheses, significance level, take a sample, find a test statistic, find your critical value or critical value, set up a rejection region, see if your test statistic is in that rejection region or not. Then you're going to either reject or fail to reject the null hypothesis, and then you make a conclusion about the claim. Like, it's a lot of stuff. But if you take it one little step at a time, and you do it enough, you practice it enough, do it over and over again, hopefully you get the hang of it. And every hypothesis test is like this. So you're going to be doing this a lot. You're going to hopefully get the hang of these steps. And this is the critical value approach, though. So like, it'll be very similar, though. It'll be the same number of steps for the p-value approach when we eventually get to that as well. All right. Thank you for watching.